Okay, we'll see how this goes. It's a brand new battery. It should work. All right, so we did one example so far of calorimetry. This is the name for this, where we're talking about heat transfer from one object to another.
What do you call it?
Calorimetry. Yeah, calorimetry. Comes from the word calorie. So that's related to, calorie is the non-SI units for joules. So this is basically the transferring of thermal energy between objects and the environment. This slide isn't super critical. I think this may come up in one of the examples or homeworks, I'm not sure. But this is just different ways to write the same equation that we've seen before using different variables. So you can write our heat transfer equation as capital C delta T, where capital C is heat capacity. Heat capacity has various units depending on what temperature scale you're using, or whether you're in SI units or non-SI units. You can also write heat in terms of moles. If you've never heard of a mole before, you need a refresher. It's a unit of measure for the number of atoms or molecules in a system. So 1 mole is 6.02 times 10 to the 23rd things. So you could talk about the number of gas molecules in a volume in terms of moles, because there's going to be a crap ton of molecules. So it's easy to use something small like a mole to describe a whole ton of things. So a crap ton, yes, that's the official term for 10 to the 23rd is a crap ton. This is totally off topic, but I was trying to decide when you have 4 kids, is that a crap ton of kids? And then if you have 5 kids, does that become, at what point does that become a shit ton? And then if you've got 7 kids, is that a fuckload? Have you at what point is it okay. I'm on video. This is great.
Or it just gets really basic. It's just a lot.
A lot.
It just comes back down.
Or a mole. You could have a mole of children. You could write your children in terms of moles. Okay, molar mass, capital M, is the mass of 1 mole of a substance. And so the number of moles in a system is little n. I know, another little n. So the mass of that system would be little n times the molar mass. And then if you wanted to throw that into this equation, our MC delta T equation, so the mass of an object is the number of moles times the molar mass. And then combining, what are we combining? The molar mass times specific heat gives us a new variable, C sub m, which is the molar specific heat. Okay, so it's basically like 4 different ways to write the same equation. These forms rarely come up. So, yeah, Chris?
Is big MC molar calorie?
Big M
Times C for molar heat capacity?
Big M times C is molar heat capacity. Oh, do you call big M times C molar calories?
Yeah,
oh.
moles times calories.
It's moles times specific heat. Specific heat is our little c. Yeah. Yeah. All right.
It'd be, for example, your unit would be mole joules per Kelvin.
Moles, joules per kilogram Kelvin, yeah. Anyway, some of these new variables we've seen show up in table 7.3 as well with specific heat. So if you see something in a problem, they give you molar heat capacity or the number of moles, then this is the slide you want to refer to. Otherwise, this stuff doesn't really come up. All right, so calorimetry, I've already kind of defined that. States of matter, or the phases of matter. We've learned this in elementary school, solid, liquid, and gas. So you can have phase changes where you go from one state or one phase to another. The important thing to remember, and I'm probably going to keep harping on this again and again, is that during a phase change, the temperature of the system doesn't change. It's working on other things. It's working on transforming into something new. So that temperature is sort of like, okay, I'm not going to change my temperature for a while because I'm busy changing my state. And until I'm done changing my state, I'm going to stay the same temperature. So remember that. We have words for state changes. We've heard of most of them. Melt, freeze. This is when you're going from solid to liquid or liquid to solid. In the case of melting, you're adding energy to your system, so that's a plus Q. In the case of freezing, you're taking energy from the system, so that's a minus Q. Vaporizing and condensing, liquid to gas or gas to liquid. And then two you may not have heard of, sublimate and deposit. So sublimate is you're going from solid straight to gas. And deposit is where you're going from gas straight to solid. And I have examples of this. Your lemonade on a hot day. Everyone's dreaming of it right now because it's a hot day. It gets water condensation on the outside of your glass. That's condensation. But you might notice that your ice cubes sort of have vapor coming off of them. So that's sublimation. Deposit is what happens to your freezer. So every time you open the door, air comes in, warm air comes in, and it builds up the frost on the walls of your freezer. So that's going from gas to solid. Yeah, Chris?
Does the book or your test ever use fusion instead of heat of fusion? I know that we.
Yep, we'll talk about that. Okay. Yeah. So that's how we define the heat change during a phase change, is using the heat of fusion and the heat of vaporization. So during a phase change, then instead of calculating Q in terms of the temperature change, now we're going to calculate Q in terms of the transformation. So the Q of transformation is plus or minus M times the latent heat of fusion if you're going from liquid to solid, or the latent heat of vaporization if you're going from liquid to gas, or back and forth. So if the phase change is liquid to gas or gas to liquid, then your heat of transformation is M plus or minus M latent heat of vaporization. And if you're going from solid to liquid or back and forth, then you've got plus or minus M times the latent heat of fusion. These are variables that are material dependent, like water. It would have a different latent heat of fusion from salt water, for example. So those you're going to look up in a table.
When something sublimates or deposits, is it 100% skipping a phase, or is it just transferring phases really fast?
It's just skipping a phase.
So with these heat transformations,
It won't do sublimation or deposit. You'd have to have a different equation.
oh, okay.
Yeah. So that gives you a clue. We're not ever going to deal with sublimation or deposit in here. Yeah.
If something's sublimated, would it be a near equivalent if you added up all the heat of transformations?
I don't know. I've never calculated it to know. I'm not sure.
Okay.
It'd be a good practice homework problem. Though you don't need to find the equation for the heat of sublimation or diffusion, but I think it might be in the book. Maybe.
I just wonder if it's less, like because it's skipping one point of transformation, does it just completely, not need that as much energy?
It may be. I don't know. There is a section on page 567 in your book that talks about it, but I haven't read that section, so your book would be a good resource to find out. Maybe it tells you. So these values you can get in table 17.4. So to make your life difficult, we like to give you problems where things not only have a temperature change, but they also go through a phase change. It may be more than one. So in order to figure out the total heat transferred between the system and the environment or two objects, you've got to add up all the phase changes and temperature changes. So let's say an object starts out down here below the freezing point. Say it's water. So you've got ice, but it's really cold ice. So it's colder than 0 degrees Celsius. And you want to melt it. So it's completely solid, and you want to warm it up to, say, 75 degrees Celsius. So you're going to have to account for the heat required just to get it up to 0. So that's the MC delta T, taking into the account the temperature change to get it to 0. There's going to be a different specific heat for ice than there is for water. So that's why I separate this from the temperature change above 0. Once it gets to 0, then it can start melting. So it's sitting at 0 until it completely melts. If it's not completely melted, it's still at 0. So if the question says, what temperature is the ice when half of it is melted? Then your answer would be it's 0 degrees Celsius, because it's going to stay there until all of it's melted. So M times L would be the latent heat of, let's see, solid to liquid, liquid to solid. So that would be the latent heat of fusion for water. And then once it's all done melting, now it can warm up to 75 degrees Celsius. Now you use the MC delta T again. This is the specific heat of liquid water, which is different than the specific heat of ice.
So my question, when you have an ice cube that's melting
Mm-hmm.
and it's wet, so part of it's already melted. The part that's still solid is still the same temperature, but the part that's melted is a different temperature.
It's all the same temperature, as long as it's a closed system. Meaning as long as the ice and the water are not losing heat to the environment.
Right, so in a regular real-life application.
In a real-life application, if you've got a puddle of water, then the edges of that water might not be 0 degrees Celsius anymore. But if it's the wetness that's on the outside of the ice cube, then you can assume the wetness on the outside of the ice cube is probably still 0 degrees Celsius, even in a real-life application. Yeah. Okay, so let's try example 17.8. And I set this problem up for you. I've given you an example of how you would set up the heat part for a melting ice cube. So I want you to try 17.8 on your own. You've got a glass containing 0.25 kilograms of omni-cola, mostly water. They're basically telling you use the specific heat of water. You can get that from up here, because that's what we did with the coffee before. It's initially at 25 degrees Celsius. It asks you how much ice, initially at minus 20 degrees Celsius, must you add to obtain a final temperature of 0 degrees Celsius with all the ice melted. And it says don't worry about the specific heat of the glass. So in order to do this, you need to know the specific heat of ice and the specific heat, or the latent heat of fusion for water. So the specific heat of ice is 2100. And the latent heat of fusion for water is 3.34 times 10 to the 5th. All right, so give that a try for a few minutes, and we can talk about it if people get stumped.